Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to start our conversation on chapter 16, talking about acid-base chemistry. So as we proceed through this chapter, we're going to be spending a lot of time bringing up our knowledge of equilibrium reactions and looking at a very specific type of reaction. So when we're talking about acid bases, I want you to be aware that we're going to be mostly using two major definitions of acid base. The first of which is the Arrhenius definition. And a lot of our acid-base terms actually date back to this definition, even if it is a little bit dated. So when I'm talking about acids, according to the Arrhenius definition, an acid is going to lose its protons when placed in water. So in this case, an acid acts a lot like an electrolyte. It can be a strong electrolyte like HCl and completely break apart into protons and chloride, or it can be a weak electrolyte like acetic acid, also known as vinegar, and break up into acetate and protons. But again, it will proceed some this direction and some back. So we'll establish an equilibrium as opposed to a more complete reaction with a strong acid. In contrast, Arrhenius bases are said to release hydroxide. So the Arrhenius acids isn't a bad place to start, but the Arrhenius bases leave a lot to be desired. So a more accurate way to talk about our acid-base reactions is instead to switch to the Bronsted definition. So according to the Bronsted definition, an acid is going to be any species that can donate a proton. So this can be something like HCl, acetic acid, or even just good old water. And in comparison, a Bronsted base is going to be something that can accept or gain a proton. So something like hydroxide, this is where the Arrhenius definition comes from, because anything that releases hydroxide releases a base. Or it can be things like a lot of nitrogen-containing species, such as ammonia, which has an extra lone pair that can pull in an extra proton to make ammonium. Or it can be things like water. Yep, water can be an acid or a base, and we're going to be dealing with that a lot through this next chapter. However, if I'm going to have any acid-base reaction, it requires the presence of both an acid and a base. I need something that can donate or lose a proton and something that can gain a proton. So in any given reaction, the acid will always be the species that loses the proton and the base will be the species that receives it. However, if a proton moves from one species to another, turns out that all reactions exist in equilibrium, which means it's possible for the proton to move right back. This means that any acid, once it gains a proton, will form a conjugate base. A conjugate is a way to essentially say that it belongs to a secondary species. So any acid will create a base as soon as it loses a proton, and conversely, that base, when it accepts a proton, will generate some form of acid that can lose the proton right back. So every acid can become a base, and every base can become an acid. Now, one of the big things we're going to be doing as we're looking at acids and bases is to try and evaluate the strengths of an acid and base. And we're going to do this by looking at the ability of an acid to lose a proton compared to the most common base we're ever going to find, water. And so this is called an acid dissociation reaction. We'll talk about it a lot more in the future. And one of the key features of this reaction is as the proton moves from the chloride to the water, it's going to generate hydronium as our conjugate acid. So whenever we're talking about an acid in water, usually how the proton moves through water is going to be as this hydronium species. This actually maps fairly well onto the old Arrhenius definition of an acid as something that loses a proton to water. That free proton is actually a hydronium atom. And in truth, and as a result, anytime I say a proton, it's pretty much synonymous to a hydronium. And I'll often be using these two phrases interchangeably. If I refer to a hydronium, you can often treat it as a proton in water and vice versa. However, it's worth noting that in truth, this hydronium is often supported by a whole bunch of extra water molecules that makes it more stable and possible. And so when we're going to be looking at the strengths of acids and bases, or the strength of an acidic solution, really what we're going to be doing is measuring the amount of hydronium present in the water, because any free protons tend to move around as this hydronium species. So monitoring its presence is really important to acid strength. On the converse sides, if we're going to look at how active a base is, we're going to essentially see how well it can remove a proton from the most abundant acid in water, which is water. And so any sort of base, when it reacts with water, will end up producing some sort of conjugate acid, but much more importantly, it's going to produce hydroxide as a base. And so this is, again, the origin of the Arrhenius base definition. Every base will essentially produce some amount of hydroxide when placed in water. So if we're going to look at how basic a solution is, we're really going to be trying to track how much of this free hydroxide is present in water. So trying to monitor these hydronium and hydroxide concentrations is going to be really important to understanding acid-base chemistry. The other big feature that you should make sure to pay attention to is that any of our acids can always generate a conjugate base. Whether it's acetic acid will generate acetate, which in and of itself can produce some hydroxide. So it can become very important whether you add acetic acid or sodium acetate solution, or this is true with any number of other potential acids or their conjugate bases, as they can quickly interconvert, because turns out there's always going to be an acid or base around in water. It's water itself. And this will become a major feature of the next two chapters. However, I want to go ahead and take a moment to talk about 7 of the most important acids and 6 of the most important bases. So as we proceed, I want you to be aware of our 7 strong acids. So essentially what makes a strong acid is they disassociate, quote unquote, completely. This means that all of these reactions are going to be heavily product favored. So our 3 of the common ones you may be familiar with are hydrochloric, hydrobromic, and hydroiodic. So all of these are simple halogen acids where you have a proton attached to a halogen. Now, this proton can go ahead and leave the halide behind, producing chlorine, bromine, or iodine. All of these are very stable species, meaning that that proton is more than happy to go hang out with water, because more or less these halides really like to be left alone. And this is really what's going to control the stability of all of these, the reactivity of these acids, is that once you get to the products, it's really not going to go back, because these halides really just like hanging out on their own. Just leave them alone. In conjunction, what we also tend to find is as the halide becomes bigger, as we go from chlorine to bromine to iodine, that hydrogen halide bond becomes longer and longer and longer, meaning that it's harder for that proton to hang on, and it's much more likely to react and fall off. All of the remaining of our 4 strong acids are called oxyacids, and they're referred to this because one of the big features of these oxyacids is that they're an electronegative atom surrounded by a whole bunch of oxygens. So the big 4 oxyacids are sulfuric acid, nitric acid, perchloric acid, and chloric acid. So if we're looking at these, all of these are highly driven by the fact that once a proton leaves this essentially oxyanion, what you're left with is a species that's more than happy to be on its own. So if we're looking at something like nitrate, nitrate is a very big ionic species in a lot of solutions because it almost always forms a strong electrolyte. Nitrate, more than happy to hang on its own. It don't need nobody. It's a strong person. And so this is going to be true of all of our conjugate bases, whether it's sulfate, nitrate, perchlorate, or chlorate. All of these more than happy on its own. And this means that those acids really don't want to be acids. They just want to be free. On the converse side, we can also look at the strong bases. They're going to follow a lot of these same sort of rules, but instead of releasing a proton completely, they're going to essentially release hydroxide ions. The big notable difference here is that they're almost always more or less just salts. So the hydroxide is often paired to one of our strong electrolytes: lithium, sodium, potassium, and barium. These are notorious for falling apart as soon as you put them in water. And this is more or less what happens with these strong bases. Once you go ahead and throw them in water, they'll completely dissolve to release hydroxide, at which point this hydroxide can react with water and produce hydroxide. Yep, that hydroxide ain't going anywhere till it can find an acid. However, there's two last strong bases, and they're kind of a notable case because calcium and magnesium hydroxide are sometimes considered strong bases and sometimes not. And the reason why is that as soon as they react with any sort of acid, that hydroxide is immediately going to react and act like free hydroxide. But in the meantime, the calcium and the magnesium hydroxides are only slightly soluble, which means that they often need a little coaxing to react as strong bases. So unless you have an acid better than water for them to react with, they're not going anywhere. However, as soon as you give them a half-decent acid, they tend to dissolve fairly quickly. Now, this brings us to the last major point. Acids, bases don't exist on their own. I throw an acid in water, it's going to release some hydronium. I throw a base in water, it's going to release some hydroxide. The real fun part is what happens when that hydronium and hydroxide find each other. Well, it turns out it's love at first sight, and they quickly react to form water. So this is going to be a very favorable reaction, as that proton can move over from this water over to make this water. And so this is going to be a fairly rapid sort of reaction. So much so that it tends to have an equilibrium constant of about 10 to the 14th. So if you called this a reaction that goes to completion, you wouldn't be too wrong, except for the fact that it turns out there's a whole lot of water. And all of this water can do the reverse reaction and produce hydronium and hydroxide. So it turns out wherever there's water, there's hydronium and there's hydroxide. There's always going to be protons and hydroxides in any solution. The real question is how much of each. Now, one of the big things that we're going to make use as we go forward is that this is a very special sort of reaction, which we're going to call the water dissociation reaction, with its own constant that gets its own name. This is Kw, or the water dissociation constant, because the chemists are ever so clever. It is one of the really kind of bottom of the end equilibrium constants. It's 10 to the negative 14th. However, since there's so much water, it means that we always have a certain degree of presence of these two species. Now, the real beautiful part is when we do the expression for this reaction. And it turns out the only things that show up in this equilibrium reaction, because water doesn't count, is hydronium and hydroxide. This means if you know the amount of hydronium in one solution, you know the amount of hydroxide in that same solution. Now, it is worth noting that like any other equilibrium constant, this will change with temperature, but at room temperature conditions, so 20 to 25 degrees, it's pretty reliably about 10 to the negative 14th. So we're going to be using this number a lot as we go forward, because if I want to figure out the strength of an acid, I'm going to look at hydronium. If I want to look at the strength of a base, I'm going to look at hydroxide. And we're going to dive into this idea a lot more next time. Till then, take care.